Hey, Jam, have you ever wondered what's in this thing?
I guess I have. I thought it was air, but it's more complicated than that.
It is more complicated than that. For those of you listening, I am holding an air duster can. Let's see if I can get a good sound on the mic.
Yeah.
Ugh, I just smelled it. Okay. So could you hear it good on there?
Yeah.
Nice. Okay. So I'm holding a little air duster can. And have you ever flipped it upside down also and seen the liquid come out?
I have, and I've also noticed that when I'm spraying it upright, the bottom gets really cold.
Oh, yes. That is something to think about too. Mm-hmm. That was my next question.
Mm-hmm.
So I always thought that this was just compressed air. But a few things recently made me curious and wondered that there might be more that goes with it. I don't use these really very often. So, and also I found out that there's a lot of dangers associated with air dusters.
I've heard that.
So,
I know that when I had to buy those that you're holding there, I think I had to show my ID.
Did you?
Mm-hmm.
That doesn't surprise me.
Yeah.
Well, let's get into the chemistry of what's up with these air dusters.
Okay, let's do it.
Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life,
the podcast to help you understand the chemistry of your everyday life.
Okay, so today's episode was inspired by a few different people. Greg S. emailed us a lot of questions in one email in 22. One of them was about compost. And now I think it's November of 22. And now another ones he asked about was about air dusters. And so that's been in my mind. And then a few months ago, my sister-in-law sent me a video, and I'm going to show you the video. And could you splice it in on YouTube?
I think I can, yeah.
But maybe you can also just describe it for people after you watch it. It's short. It's 7 seconds.
Oh, she took this video herself?
Yes, this is from my sister-in-law. She took this video
Even
at
better.
work.
I was worried that it was like somebody else's source, and so I thought we might have to get permission, but it's hers. Ah, yes. So she sprayed it upside down, and the liquid came out onto a surface, and then it quickly disappeared.
Yes.
Okay.
Okay, so she sent me that and said, why does it do that? Okay, so that is something that happened. And then my sister has recently gone through so that was my sister-in-law, and this is my sister in blood, in birth sister. So she recently had to go through a surgery, and so she had a cast on it, and she was using the air duster to try to scratch an itch, basically, just blow air down there to try to, which I was like, oh, that's a good idea.
Yeah, smart.
Not smart, because she got hurt, a wound from the air duster. And she was like, what was the wound? Was it like a cold burn or what? And so those three things came together, the sisters and Greg, made me realize it was time, and that this wasn't just CO2, which is what I kind of thought it was all along.
The sisters and Greg.
The sisters and Greg. So this episode is for them.
Okay.
So I'm going to start, I think, with the 2 chemistry lessons that I think will shed light onto what's happening here. And then once we have the foundation of the 2 chemistry lessons, explain what's actually going on, and then answer the questions.
Okay.
And the questions that we'll answer is, why does it get cold on the bottom? What's that liquid stuff that comes out? And what's actually in there? And then what happened to my sister?
Okay.
Okay.
Before we get all the way into it, I wanted to give the caveat. Y'all can probably tell my voice sounds like it's kind of going out a little. I'm most of the way, almost all the way recovered from being sick, but for some reason my voice sounds like I'm in the throes of it. But really, I feel great. Hopefully, because I don't do nearly as much talking as Melissa does, hopefully it'll last the whole episode and won't cause any problems, and just be a little more enjoyable to listen to,
Yeah, it's kind of got a nice gravelly quality.
But so just fair warning, if I start sounding worse after we're talking for a while, very sorry. Couldn't be helped, but I feel great.
Do you have some kind of hot beverage to soothe your throat?
I do. I got some decaf coffee here.
Nice.
I'm not sure it's the most throat soothy beverage you could ever pick, but just the warmth of it is helpful.
Yeah, the warmth is helpful.
Yeah.
Okay, well, so here's your first chemistry lesson. And you kind of know this already, but just kind of a reminder and a new way to think about it kind of is molecules that are in the gaseous state, they're really far apart.
Mm-hmm.
And so they're not really like one entity. It's not like, oh, there's liquid water in one area, in the air. There's like one water molecule and then a bunch of empty space and then another water molecule. Kind of like very far apart, lots of empty space.
Right.
And then if you can get them closer together, then they are close enough to where there starts to be some electronic attraction between them. Like the electrons in the molecules oftentimes sort of make poles where there's like a partially positive part, partially negative part. They start to become attracted to one another. Like they'll line up in like sort of nice repetitive ways and make one entity, which would be like a liquid state.
Right.
So there's two ways really to get these molecules close together when we go from gas to liquid.
Okay.
Two main ways, I guess, that we think about is one, really we just have to take energy out of them, making them like, for example, colder. And so that's like when condensation happens, where like air, the water molecules in the air condense on a glass. It's because it's getting colder, so they're losing energy, so they're sort of coming together. So that's one way. Another way that we don't talk about as much is pressure. So if you literally just put pressure on something, it'll compress it closer together.
We did have that one episode that was about pressure and temperature, about the car tires.
Exactly.
Right? That had kind of both things at play a little bit.
Yes.
Okay.
And so, yes, if you have something with more pressure on it, the molecules will get closer together. And if you put enough pressure on it, you can actually put something that should be a gas at a certain temperature all the way, push it down enough that where it becomes a liquid. And so you've probably seen that, like, I can't think of anything off the top of my head where we would see that in a day-to-day life. But we have talked about it before. But yeah, so if you put enough pressure on something, even say like if you had, in theory, something that was a gas at room temperature, you could put enough pressure on it to make it into a liquid. But it would have to be oftentimes a lot of pressure. It's usually like an artificially put on pressure.
Yes. Oh, you know what? I remember doing as a kid that I thought was so fun is like I would blow a lot of, like, take a empty water bottle and like put a lot of like air into it at as much high pressure as I could, and then twist it. And sometimes the little bit, I think it's mostly a little bit of the water that was left in there that was kind of vaporized, would condense on the side.
Yes.
Have
Like
you seen that?
if you blow into it, like you blow air into it, there's water molecules in your breath at a higher concentration.
And then putting the lid back on and then twisting the bottle, it was kind of like really pushing them together.
Yeah, that would probably work. That would probably make some of the water molecules condense down into liquid, or at least more than would be if you hadn't put it under pressure.
And it was just like a tiny amount.
Yeah.
So it was just like a little bit of like, oh, that's interesting. Where did those droplets come from? They weren't there a second ago.
That's a good example. That's a really good example.
But yeah, that's weird. I can't think of another way that would have just like something like that would have happened in my life. Like condensing a gas to a liquid because of pressure.
It's hard to think. I can think of a lot of examples in chemistry, but it's hard to think of them in day-to-day life. So I think you have a concept there.
Okay.
So the second lesson, and we've also talked about this, is if there's molecules in one area that have a lot more energy than in another, or that are in a much higher concentration than another, if you sort of put those near each other, they will try to even out. So the way I thought about this, and I don't know why, but I think I used to play this game. I tried to look up the name of it. I think it was called Jazz Ball. Did you ever play that?
I don't think so.
It's okay. It doesn't matter. It's just balls bouncing around like this thing, and you had to whatever. Anyway, but if you imagine a chamber or two chambers, I guess, right next to each other, and they both have a bunch of bouncy balls bouncing around in them. Okay. Actually, we'll say one has a bunch of bouncy balls bouncing around in them, and the other has no bouncy balls bouncing around in them.
Okay.
and then there's a partition between them, and then we take the partition out, what immediately happens?
A lot of the bouncy balls in the other chamber start bouncing into the empty chamber.
Right.
The one that was empty.
Yes. And so molecules will do that same thing.
Mm-hmm.
We've talked about that before, like when you have something that's really hot and you put it into a room that's like cold, you know, the hot thing will
It'll
dissipate out.
Yeah, I see. Okay.
Mm-hmm. So the same thing happens with molecules. If you have molecules in one high pressure area and then you make a space for them to move into a lower pressure area, they will do that.
Okay.
So those are two chemistry lessons that you kind of already know, but I feel like they're good to have on your mind.
Mm-hmm.
And the second one you see all the time. Like think about water balloons. If you stab it, it's because there's like high pressure. You put a hole in it, the air is going to escape out, or even just regular balloons are in a high pressure area. Put a hole in it, the air is going to rush out. Anytime you have one thing under a lot of pressure and another thing like outside of it that's not in a lot of pressure, as soon as you make a pathway for the high pressure thing to get some relief, it will. It's the state of things, like naturally in chemistry that happens.
You know, one of the funny ways that I've encountered this in my life a lot recently is that, you know, it's not hot right now, but up until a number of weeks ago, it was still quite warm here in Texas.
Yes.
Even more so in summer, of course. But with the water bottles my kids have right now, they have some metal ones. Good. They have this way of closing that, and they have a straw. If we have closing where you clamp it down and then it kind of clamps close the like silicon tip of the water bottle straw thing.
Yep.
And then when you open it, it undoes that. But what's happened several times is I fill their waters up and they're at their coldest they're ever going to be. And then we go about and do some stuff and they get warmer in the hot car or just out and about or whatever. And what I believe is happening is the little bit of air that is in there that was colder has gotten warmer and wants to take up more space and spread out more.
Because they have more energy.
But it can't.
Yep.
Because it's closed and sealed.
Yes.
So as soon as they open it, it has the ability to, but what it actually does is it can't go up. It pushes down on the water and the water sprays
comes out the straw.
And it sprays up at my kid's face.
Yep. That
many times they'd open it and be like,
same thing happened to me on an airplane because when I have an airtight water bottle and when you open it on the plane, the cabin pressure is less than the pressure was on the ground.
Oh, yeah.
Whenever I closed it. And I always think, I need to remember to open this whole thing up before I open the straw part. And I never do. And then it always shoots water out. And it's very dramatic.
Yeah.
And I literally was on an airplane like 2 days ago when that happened.
Oh, my God.
So, and yes, what you're describing of like when the air rushes out, it pushes the water out too. Is that often happens. Yes.
Yeah.
And I will say also, like in a bottle like that where there's some liquid and there's some air, as things heat up, sometimes some of those water molecules will also turn into more gas molecules as they get energy into them. Yeah. It sort of depends because then boiling, we've talked about before, is when the water molecules on the surface have enough energy that they're like equal to the vapor pressure. And so they're able to become vapor essentially. Right. So as more of them heat up and escape the liquid form, then they start to exert pressure back down on the liquid. So then the vapor pressure is always getting, the atmospheric pressure is always getting more and more and more and more. So to overcome the atmospheric pressure, that vapor pressure has to be higher and higher and higher. So it's very complicated in terms of what's actually happening chemically. Yeah. But that concept is a really good analogy for what's happening.
Okay.
So now let's get back to our canned air. I don't know if you could hear that. I tried to shake the liquid in there. So what is in these air dusted cans? It's not air like we think of. So normal air that we think of has carbon dioxide, nitrogen, oxygen, water, like all kinds of things in the air. And, they're the far apart molecules with lots of empty space. That's what we're used to having in air. So what we've done instead is put something that is a gas at room temperature like our air is, but it's not air specifically. There's certain molecules that features that we're looking for. I'll tell you what they are in a minute. It's something that would be a gas at room temperature.
Okay.
But it is a relatively high boiling point compared to something like carbon dioxide. So carbon dioxide, dry ice, its boiling point is like in the negative 70 area or something.
Oh, I see. Yeah.
But if we can take something that has like a pretty like just barely lower. So we'll say like in the 50 degrees Fahrenheit, or I think that's like maybe 10 degrees Celsius-ish, maybe in that range, maybe a little bit higher. But it's like not too far below room temperature. So we at room temperature only have to put a little bit of pressure on it to force it into its liquid state.
Right.
And that means we can condense it down pretty easily and fit it into this, smaller area that is a can.
Okay.
So we take a type of gas molecule that is relatively easy to condense down. You don't have to put a ton of pressure on it to make it force into the liquid state. And we put it just like a water bottle into a can.
Okay.
And then the difference is the empty air that is like the empty space at the top of your water bottles. Those probably just have regular air in it. The empty space at the top of this probably doesn't have a ton of regular air in it. The empty space at the top of it would start to fill up with molecules of whatever this liquid is that's trying to be a gas at room temperature until it's filled up all that it can in that area. So in this can, we have actually not gas, but liquid. And that's why you hear it.
Yes. Could I make some guess about what liquid it is?
Yes.
Or do you think there's a chance I could get it right?
I don't know. Maybe.
Is it pretty out there?
There's a lot of options it could be. There's like a class of molecules that do it. What's your guess?
Well, I guess that makes more sense. I was thinking that I could try to pick, like kind of go through some elements that I know are normally gas at room temperature.
It's not just one element.
But it's a number of things. Okay. Dang. Okay, never mind.
So the element that I guess I can go with, the molecule that's most often used is 1,1-difluoroethane.
Okay.
So it's not too dissimilar from a lot of forever chemicals, which are polyfluorinated alkyl substances.
Great.
I know, not great, but not as bad as those. There's not, because it's not the big long polymer chains of them. It's like shorter bits. But like ethane at room temperature, propane, butane, all of those are gas, But adding these fluorines will change the properties of them, changing the molecular weight of them actually changes the boiling point. So there's a lot of underlying chemical principles here. But so they use these, often they have one fluorine or two fluorines, one or two chlorines, something like that. There's a whole class of them that are relatively easy to compress from a gas into a liquid.
Got it.
But it's under quite a bit of pressure, not as much pressure as like if you had an oxygen tank.
Right.
That we're trying to compress air in or whatever, or a carbon dioxide tank. In theory, those would work, but it would probably take a lot more pressure.
That's what I was thinking. I was thinking, I know about like liquid oxygen, liquid nitrogen, like liquid CO2 or whatever. And I was like, so I know about those. I wonder if I could run through the Rolodex in my mind of other kind of basic elements and see if it's one of those, but it wasn't.
No, yeah.
But I was assuming for some reason that it would be like, it's actually argon or something like that.
Yeah.
Like, oh, okay, cool.
Well, and that's what Mason thought too. He's like, it's probably just compressed carbon dioxide, but that takes more pressure to keep a can of those. And then that becomes really dangerous because if you accidentally release the pressure, it, goes kind of crazy.
Right.
So these, I think, they have to be under a little bit less pressure. It's still under pressure, but I don't think it's as intense.
Got it.
So when we depress the button, what essentially happens is...
Oh, yeah, that straw kind of comes out sometimes if I haven't used it in a while.
When we depress the button, what happens is we essentially lift up the partition between the two chambers. So the can is a chamber that is full of a bunch of gas molecules and liquid. and it is compressed under high pressure. And when we push on this button, it opens the gate. And then now there's an open space between a relatively low pressure area that we're in, that's regular pressure, and this very high pressure area. So the gas molecules immediately see like, there's a way out, and they're rushing towards that.
Yeah.
And then that means that the headspace that was here, that was kind of empty that was like empty air, not liquid, full of molecules that had evaporated from the liquid. Now there's an absence there. So then there's less pressure within the can, even when we release this. And so then the boiling is able to happen where some liquid in here is able to then turn into gas.
I see. Yes.
So we release some of the gas molecules that naturally rush out in a way that you would expect. And then some of the liquid evaporates up, and then you get more gas in this top part that then would be able to escape out again next time. And then we get to everything being back under pressure.
Got it. And that's why turning upside down releases liquid instead.
Yes, because liquid is denser than air. And so when you flip it upside down, it's still the gas molecules are trying to get out. But they're pushing liquid out too, just like when you shake up a soda can, it's forcing the air bubbles out, but it's bringing the liquid with it.
Right.
Because the liquid is denser. And the reason it evaporates so quickly is this type of liquid wants to be a gas at room temperature anyway. So as soon as it gets to room temperature and pressure, it is going back to its normal state.
Okay. Yeah. Interesting.
It's like you've set it free. So that's the chemistry behind sort of how this happens. I think the way you described it was really good. You answered one of the questions. But the thing that might be kind of hard to wrap our mind around is why it gets so cold. And the reason for that is, if you think about what's happening here, the liquid is essentially boiling.
Right.
And to make something boil, we have to put energy into it. Energy is going into that liquid to make it boil from its surroundings. So it's taking heat from the surroundings, which to us feels like it being cold. So normally, like boiling water happens at a pretty high temperature. So to us, it seems hotter.
Right.
But if you think about what you're doing with the flame is you're just putting energy into water to make it boil. You're just heating it, heating it, heating it, heating it. So it's taking heat from its surroundings, just very hot surroundings.
Yes.
And putting it into the water. Well, here the boiling has to happen. There's no flame. And it doesn't really need flame because it can boil at room temperature, but it needs the temperature. So it takes the heat from the surrounding areas. And to us, that feels like cold.
Interesting. But it's weird because it only does that after you've released some. So it's because it's doing that again to fill up that space, right?
Because so after you release these gas molecules at the top, then there's empty space here. So then the liquid starts to become a gas to sort of fill up. And so the boiling happens after.
Got it. Wow.
Sounds like there might be a leak in this. I probably should stop messing with it.
Interesting. I mean, I hear. Weird.
Did it stop?
It's been sitting dormant. I can hear it still.
Okay.
Well, it's been sitting dormant in my drawer for a while, so I wonder if it's just getting some action, and who knows how cheap the little like barrier is if it's like.
It's kind of stopped. Maybe we could just hear it boiling in there.
Oh, maybe so. Maybe so.
Who's to say?
Yeah.
Anyway, I should probably stop messing with this because this is a dangerous chemical, and it's crazy to me that they sell it on a shelf now that I know this.
Yeah, that seems interesting.
Yeah.
I mean, it'd be great if it was just like, and wouldn't you know it? Such and such element happens to have the boiling point of, like, even if it was just like, 0 Fahrenheit.
Well, even just the idea that
or Celsius.
What's happening in here is like something under high pressure that we sell. It seems crazy.
Yeah.
I'm like, this could go really wrong. Like if a kid picked this up and put it in their eye and then squeeze the trigger.
I wonder what the pressure is. Like,
I don't know.
The PSI or whatever.
But anyway, so all that to say, that's why it gets cold. And let's see. The other question is why liquid comes out. We already talked about that. And then what happened to my sister?
Oh, yeah.
Why did it burn her? Well, that air, as it comes out, is evaporating very rapidly. So it's taking as much energy as it can. And so right there at the point where it comes out, I saw one video from the American Chemical Society that showed that it can get down to negative 40 degrees Celsius.
Whoa.
Is it negative 40 or is it 40? It is negative 40, which can cause frostbite instantly.
Oh my gosh.
So I wonder, so that's one thing that could have happened, is that she could have gotten frostbite. The other thing, but it would have been mild, and I learned that that's called frost nip. But the other thing that could happen is...
Oh, after that song. It's named after that song.
What song?
Jack Frost nipping at your window.
I knew that was coming.
It's crazy that literally is those two words are together in that song.
Jack
like that.
Frost nipping. Yeah. The other thing that could happen, and I read an article about this. This is very sad, but I guess some teenagers, especially, the specific demographic is teenagers, 8th grade, 10th grade, and 12th grade. Actually, I think were the most often that this happened to.
Weird.
Of Caucasian teenagers in houses well above the poverty line. Use this as a drug, as an inhaling drug, huffing. Yeah, that's what they call it.
Right.
And so it was a case where they were looking at a teenager who had a chemical burn all on her face and neck from that. But it didn't show up right away. It started to get worse after, it seemed like. And so what can happen is the fluorines are really good at scavenging for hydrogen and things. And so you can actually get an acid burn. It basically makes an acid on your skin.
Oh, wow.
And burns you chemically. So you can either get a cold burn, quote unquote, frostbite, or you can get a chemical burn from the reaction of the fluorocarbon with the air. It can cause a chemical burn on your skin.
Wow.
And I think maybe it doesn't initially, if it initially touches and there's not much of an impact, and then over time, I don't know. Gosh. It seemed like that was how it played out, is that it wasn't noticeable at first. But so I don't know what happened to Renee because it happened within her cast. So we can't see it to assess. But it could have been a chemical burn, or it could have been
a little frost nip.
Frost nip. Just in a very concentrated area right there where it came out, depending on how she used the compressed air. So don't use the compressed air in your cast.
Yeah. Good.
Or on your skin at all.
Idea. Yeah, good idea.
And I can kind of smell it. I haven't used these almost ever. And so when I sprayed it on my mic and then leaned forward, I smelled it. And it is supposed to be relatively harmless compared to a lot of other things we could be breathing in. But it's still not great for you to be inhaling really anything other than air. So, and definitely not in high quantities like children are doing to abuse it, substance abuse.
I remember hearing a horror story about that at one point, but it was one of those someone's mom told somebody else's mom, and my mom told me when I was young. And so I remember feeling okay, don't mess with this stuff. That's all.
No, you could get really bad chemical burns, and you can have lots of bad things happen internally. There's lots of, and I linked to some of them, articles in peer-reviewed medical journals where they were doing case studies of what happened to people of chemical burns and things from specifically air dusters.
Wow. Dang. Gosh.
And not always in they were abusing it and trying to huff it or whatever, but also just in using it.
Yeah.
Yep. So you should be careful with that.
I will, definitely. I really wouldn't prefer to use it, except that there's not anything quite as good at getting stuff out of keyboard nooks,
Yeah.
But they actually have seen ads for I just didn't want to spend the money on it, but I've seen ads recently for these very small little battery powered air compressor thingies, a little tiny blower. And you just like
a leaf blower, but tiny.
Yes, but tiny.
Yep.
It has a tiny little nozzle to it, which is great for keyboard stuff.
Yeah, that would be perfect.
Yep.
And safer.
And then it's just taking the air around it and doing that instead of some other thing. So that'd be cool.
And Mason, I asked him if he had one of these because he always has stuff like that. And he was like, no. And I was like, well, you said you used compressed air to do something the other day. And he's like, yeah, we have an air compressor. And I was like, oh. So that is a good example of the energy that would require to concentrate air down and then blow it out. It's like you have to use energy to concentrate air down and then force it out at a specific speed, you know?
Yeah.
So, so I have really actually never used an air duster, and I just have a dirty keyboard.
Mm-hmm.
Maybe I could see myself using those little putties, you know, those like sticky, those like putties but otherwise I just let myself have a dirty keyboard.
And you know, what's actually kind of satisfying is I watched a guide the other day. Not everyone should do this. You have to be very careful, but watched a guide the other day about how to get the MacBook keyboard keys up. You can just like
pop them up.
Mm-hmm. And, just clean under there, and I used a little brush I have. And then with that, honestly, if you're gonna brush it, then you can almost honestly just be like, and just blow the stuff you just brushed off away if you want. And it works great, but it's very satisfying to do. So it's like kind of nice to get under there and get that stuff out.
Yeah.
You know? I bought this tiny little cleaning kit on Amazon.
That's satisfying.
That has like some different sizes of brushes and like a little kind of pick thing if something's like really dried on that you need to kind of like get off or whatever. But it's very satisfying to do.
Yeah, I wonder how my keyboard gets so bad, and then I'm like, oh, I use this computer for literally everything.
Yeah,
so
same.
That's why.
Sometimes I look at other people's computers, I'm like, oh man, yours is very clean. Mine looks like a piece of trash computer. It's like
maybe when I get a work specific computer, it'll be better.
Yeah,
you know,
maybe so.
Okay, well, you kind of participated in this, so I don't know if we have as much of a teach back as normal.
Right.
Do you want to just give us a little summary and make sure that you're tracking with the chemistry behind it all?
Yes. So there are many things that want to be gas at room temperature. Mm-hmm. But what we're trying to do here is make gas become gas moving very strongly in a direction at will when we want it to.
Yes, yeah.
And without any batteries or electronics available. It's just trapped in there. So in order to do that, what they had to do is make a certain molecule combining certain things together, which is fluorines and what else?
It's
chlorine?
The most common one is 2 fluorines on 2 carbons, basically.
All right.
But you can there's lots of combinations. I read out, there's a whole list of and it's linked in one of our papers that we link in our references. There's a whole list of here's the name brand and here's the thing they use.
Got it. So they found the perfect thing to have the boiling point. That's what we need. That makes it kind of the easiest.
Yeah.
So they could trap a liquid form of this substance into an airtight can. It wants to be gas, but it can't under pressure trapped in this can.
It does a little.
At the very beginning, I guess. It's super full, but has a little.
Very little bit of gas at the top.
The rest is stuck being liquid.
Yes.
And so when we pull the trigger on these little cans of air, all the molecules that are in the can that are in liquid form are stuck so close together. They really want to be gas, but they can't be. There's not enough room. The gas is also stuck closer together than it wants to be, but it's still in gas form. And it's ready to escape as soon as the gate opens.
Yep.
They're ready to break free. So as soon as we do that, gas comes out, especially if we hold it upright, then liquid won't come out, just the gas will, because it's the top.
Yep, because it's less dense, because it's by nature spread apart more than the liquid.
It comes out, cleans our keyboard or whatever, and then we let go of the trigger, and it's closed back up. And then with the space we just sort of created in there, more of the liquid can boil.
Yep.
And take up that space, that top layer of gas space.
Mm-hmm.
And that process, as counterintuitive as it sounds, of it boiling feels cold to us because it is taking heat
Yep.
from the environment,
Yes.
which is everything's always doing, I guess.
Yeah.
Everything wants to kind of share and
Even things
things
out.
out. In this case, we've just changed it, so it's having to sort of react.
Mm-hmm.
And the fact that the boiling point of this liquid is so low, it can just take some heat from around it, boil some of its liquid,
Mm-hmm.
take up that gas base, and then it feels cold to us. And it's not good for our skin.
Yep. Because it's very, very cold.
Is there anything else that I missed?
No.
And
I think that was everything.
And we couldn't just do this with any other, because of all that. We couldn't just with any other just random gas, because it'd either be way too high of pressure that's not safe to just have laying in your drawer in a cheap little aluminum can, or it would just be way too expensive, I guess, would be some part of it too. I feel like to handle something like this, that whatever the facility is making it only has to get it below a certain temperature to make it liquid. That's probably way easier.
That's what I think. My guess is that the way that this is probably often created in manufacture, this is a guess, is that they have these cans, they pour liquid in, they seal it at a cold temperature. So they get it to be liquid. Like maybe it's like refrigerator temperature. Maybe it's like freezer temperature. It's like in the 30s. It's cold. They pour it in, 30 Fahrenheit. They pour it in and then they seal it. And then when it comes back up to room temperature, it's like they've probably done the math to know that, oh, we can put exactly this much in. And so it'll still be safe once it comes back up to the right temperature. It won't put too much pressure that it'll explode. Like I'm sure they've calculated exactly how to pour the liquid in to a level, seal it, and then so it's safe. I bet it's something along those lines is what I guess. Yeah. That's a guess that I have. I don't know. But it would have to be, I think that would have to be a very careful process because your aluminum would have to be rated to hold whatever pressure it puts out. Because if you heat a closed container, that's a bomb. Or maybe there's like a valve that as it heats up, they let a little bit of pressure out or something. You know, there's something that there's like, they've probably thought about all this in the process. But my guess was, oh, I bet they just fill that can with liquid like it's a water bottle or something.
Yeah.
You know?
Interesting.
So that's what I think. I don't know, though.
Yeah.
Who's to say? So now we know.
Now we know.
And I would recommend not using this compressed air, in my opinion. If you have kids, I wouldn't want it around them. And if you can clean your keyboard any other way, get one of those cool little tiny air compressors.
Yeah.
Get one of those little putties like they use in your car cup holders. I think that's probably going to be a safer option and probably better for the environment. So that's what I would use.
Yeah, that's a good idea. I also I don't do this much anymore, but when I used to do a lot more film scanning, there was a huge importance in being able to get all little tiny fibers of dust and clothing off the scanning bed. Because you're about to do a super high res scan and you're going to see all that.
Yes, yeah.
That's kind of hard because like having something really forceful was the best.
Yeah, and it doesn't leave any residue.
Right.
So anything else, it's better if it's like no water, you know, and the compression. So yeah.
But now that those little pocket air compressors are so much more common, maybe they'll be super affordable and I just get that.
Yeah, and there are definitely specific uses for this that I think, oh, this is probably like that.
Yeah.
It's like where it's like there's no water in here, and we can do a high pressure blowing off of this thing, and it doesn't leave any water droplets or anything.
Yeah.
But to clean your keyboard, you don't need that.
Right. It's not all about precision and stuff and keyboard cleaning.
Yeah.
Yeah.
So I like reading about this. I'm like, this is kind of crazy that they sell this that they sell this in stores.
Yeah.
Because it does seem like it poses a lot of risk. And there were a lot of the number one articles that came up when I researched this molecule was stuff about substance abuse, especially in teenagers, but not just in teenagers. So
I wonder how much the must be 18-year-olds to buy this. Wonder how much that's helped, if it helps at all.
Yeah.
I'd just be curious. I'm like,
Me
I'm
too.
sure that, there's a good number of people who are just getting it out of their parents' desk or teacher's desk. But if you can't buy it yourself, does that help a lot? And
Yeah.
when did they start that?
Yeah, that's a good question. I don't know. And I wouldn't be surprised as it seems like they've like shifted away towards things that could cause like any damage with the ozone and things like that. But I think there's probably still environmental concerns with this, and that over time that this is going to be sort of phased out.
Mm-hmm.
That's a guess that I have.
Yeah. Seems like a smart guess.
But for now, or like maybe it'll be like, oh, this is only for use in industry or something. But for now, yeah, I have been fine for the last 33 years not using this.
Yeah.
So, yeah. So that's your little chemistry lesson.
I love it. Very interesting.
I don't think I have any categories, but I thought this would be a good place to wrap up and just shout out our fun family things with. Do you have any like, oh, I used to do this with air compressors? Or with like, did somebody said that them and their siblings used to have fights with it, which seems
Interesting.
crazy.
No, I don't think we did that. I'm trying to think.
It's fine. You don't have to. Unless there's something in the forefront of your mind. I don't have any real memories with this. The one with Renee, I thought was funny.
Yeah, that is definitely funny. I don't have anything.
She is also a grown adult, which I think is even funnier.
I don't have anything that like I would have thought the same thing. That's like such a common mistake to have made. Be like, oh, I have a cast and it's itchy and I have this. It's like such a very, 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 anyone could have made the mistake.
Yes.
And it's a bummer that then it's like she is already recovering from something and then she got a little burn of some kind. So I could very much see that happening to me. Thankfully, I have not been stupid with compressed air in the past. Although, one thing I've noticed is that the way that straw on that one popped out, I do have a memory of somebody doing it to kind of like put something in the straw and shooting it out. Almost like a spitball in a straw or something. So the straw's not very big, but it's so easy to put a little something and shoot it. So I have a memory of one of my friends doing that. But yeah, I'm glad I didn't do too much experimenting.
Me too.
With what could be done. So.
Definitely. Yes. Yeah. I also, though, I remember hearing kids doing things like that. It's like, oh, we got some paint cans or whatever. And I just remember thinking, that sounds dumb.
Mm-hmm. That's
not really appealing to me. So I think that probably helped me out a lot.
Yep.
So, well, I think that's a great place to wrap it up.
Okay.
Thanks for learning chemistry, and thanks to the sisters and Greg for asking questions about this. And now next time you see a keyboard duster, hopefully this is a fun answer for you.
Well, Greg and the sisters, you also form a band because that's a great name.
I know.
And thanks for asking the question. Thanks for teaching us, Melissa. If you have a question, a thought, an idea, something you wonder, is this chemistry? It probably is. And we'd love to hear your question. We love taking questions for totally new episodes like this one or a follow-up to something. And we can talk about that in our Q&R Ask a Chemist episodes. So send those to us, please, on our website at chemforyourlife.com. That's chemforyourlife.com to share your thoughts and ideas with us. If you'd like to help us keep our show going and contribute to cover the costs of making it, you can join our super cool community of patrons on patreon.com/chemforyourlife. You get cool things of just ways of us saying thank you. You get an ad-free version of the show, a feed of the show. You get some perks, some thank you notes, a little behind-the-scenes things, and a bonus secret only for our patrons episode every month. And just stuff like that, ways of us saying thank you because you are helping keep the show free for everybody else and keeping it possible in the first place. So thank you for doing that. We love our patrons. But if you are not able to join that, again, we'd love for you to. But if you're not able to, you can still help us by subscribing on our favorite podcast app, rating, writing a review on Apple Podcasts or Spotify, and subscribing on YouTube to our YouTube channel and leaving a comment over there telling us what's up, asking a question, giving us some feedback, whatever it is. Those things help us to share chemistry with even more people, help us to be discovered, help people to find our show and have chemistry in their everyday life also.
Yeah. This episode of Chemistry for Your Life was made possible. I've been messing this up a little bit lately. So let's start again. This episode of Chemistry for Life was created by me, Melissa Collini, and him, Jam Robinson, who is our producer and responsible for all this amazing sound quality that you hear, even this apple crunching that you may or may not hear in the background. But as Jim said, this absolutely would not be possible without our financial supporters on Patreon. So those people who made this possible on Patreon, our community, are Julie S., Heather R., Autoclave, Chelsea M., Dorian V., Scott B., Jesse R., Sierra L., John T., Jeanette N., Cullen R., Erica B., Elizabeth P., Sarah M., Rachel R., Latila, Katrina B., Suzanne P., Venus R., Lynn S., Jacob T., Brian K., Emerson W., Christina G., Timothy P., Stephen B., Chris and Claire S., Chelsea B., Abishai B., and Hunter R. Thank you so much for all that you do to make this show possible and for your support. We really appreciate you, and we would not be able to do this show without you.
And if you'd like to learn more about today's chemistry lesson, you can check out the references for the episode in our show notes or in the description of the video on YouTube.
Yay, chemistry!
Yay, chemistry!